Hey students, I got a request here to try another homework problem. It's number 23. Oh, it's from chapter number 36. Let me go ahead and give it a try. And we'll kind of put this in this category because remember, we're doing geometric optics here in chapter 36. And so this could be a mirror. This could be a lens. Or this could be a single refracting surface. And I believe that is what it is for this case. It says here a glass sphere, and we give the index, and a radius of 15 has a tiny air bubble that is 5 centimeters above the center of the sphere. The sphere is viewed looking down along an extended radius containing the bubble. What is the apparent depth of the bubble below the surface? All right, so maybe I'll kind of draw a picture. Here's maybe the part of the sphere. Maybe the center is down here. And they say this little air bubble, maybe it's an imperfection, or maybe it is something to observe. Maybe you've seen these ones. In fact, your author here in chapter 36 does a good job in this section. I guess this is example number 36.6. But he shows this spherical surface, and it looks like we kind of have a rare coin or something embedded in it. And so that way it can't be touched, but it can be viewed. And as you'll see, it has a magnifying effect. And they do a good job of showing the diagram how the light rays would come out and then bend away from the normal, having the appearance of coming from right here. So this would be Q, and so Q is a smaller number than its distance. Looks like its distance is actually 2 centimeters. Radius of curvature is 3. And actually, that's about the same proportions that we have here, if you 15 and 10, because that's what we have in our particular problem here. So I'll start off by saying, this distance here is 10 centimeters because they said this was 5. I guess I need to check that. Has an air bubble 5 centimeters above its center. So it's 10 centimeters from where the light is going to come up. Maybe I'll do the light in red here. So the light's going to come up and then bend away from the normal, come up, bend away from the normal, and appear to be coming from still inside of the sphere, but at some smaller distance than 10. So this would be Q. And getting our sign convention straight, hopefully Q comes out to be a negative number. And in fact, that's probably what we should also point out here. I think I'll have to jump back to this table 2, where it says, here's your P, your Q, your H, and your R, and when are they positive and when are they negative? And they were, of course, derived for a case like this. So it looks like we're going to have the opposite. That is, our radius of curvature is going to be on the other side. So it even says here R. So R is positive when the center of curvature is on the back of the surface. I like to say where the light actually goes. So in this picture, the light comes in, hits the refracting surface, and goes over here. So over here, R and Q is positive. And over here, R and Q is negative. Now, that can be confusing because P is positive over here. So it's not like all the quantities are all positive over here. In fact, on this side of the refracting surface, P is positive here and Q is negative here and R is negative here. Whereas over here, R is positive and Q is positive. And let me not get into the P being negative quite yet. That's not needed for this problem, and that's a much lengthy discussion that is covered in other problems. But as I read this here, I need to say that R is going to be a negative number. Negative when the center of curvature is in front of the surface. So as it is heading towards it. All right. So in our case, that's what we have. So we're going to have R as a negative 15. And we're going to have P as a 10. We're going to start in the glass, so that'd be N1 as 1.5, and it's going to go into N2. And I'm not sure if they actually said air, but I think it's kind of indirectly applied. A glass sphere, radius 5 or radius 15, tiny air bubble. The sphere is viewed by looking down. So I guess it doesn't really say you're holding the sphere in the air. I guess technically you could be underwater looking at it, but I guess I would say maybe the problem could be more clear that you're holding it in the air, but that's reasonable to imply that you're holding the glass sphere in the air. So this would be N1 over P plus N2 over Q, and then an N2 minus N1 over R. And of course, this is it, the apparent depth of the bubble. So we're looking for a Q. And so putting in these values, this is 1.5, this is the 10, this is the 1, this is what we're looking for, the Q. This is then a 1 minus a 1.5. Then this is the negative, and that might be kind of the hardest part of any of these optics, is keeping our sign convention straight. And now solve for Q. All right, so grabbing my calculator, maybe I'll just do this numerator. 1 minus 1.5 is obviously a negative 1.5. If we divide that by a negative 15, this whole thing is positive 0.033333. Then I'll subtract, when I move this to the other side, 1.5 divided by 10. So that is the reciprocal of Q. Hit the reciprocal key, and I get Q as a negative 8.57 centimeters. Yay! So good. It did come out to be a negative number. And so Q, the depth inside, is 8.57 centimeters, the apparent depth. Where does it appear to be? And, of course, a negative number. All right. Hope that helps. Take care.